minus 4, and that happens to be exactly what you have up here. So no arc sign prep necessary. Waiting for the, you guys all figure this out on your own? Clean says maybe, maybe not. Okay, so yeah, so that means that I really just need to put in a -2. Shouldn't this be a -1/2?
Oh yeah, I left the sign off. Sorry.
This should be a -1/2. And then it's just a straight up du over root u problem. I think it was maybe over here or something. So, so then that's u in there 1/2. So yeah, so we get 1/2 negative root u. So it's just that. Cool. Okay, Dean Johnson, getting pretty good at this. I don't know what that smile means. All right, can we take back out the packet? We're gonna do a couple more of these. We're gonna go for like 8 more minutes. Yes. Oh yeah, can I have this homework? Yeah. Let's take back out that packet called antidifferentiation by method of substitution.
Oh, yeah.
And let's do like 2 or 3 more problems, and then we're going to learn something new.
Is it filming? Hi guys.
Yeah, it looks easy.
It's like Legos. Said engineers. Like programmers just not an option.
So I thought we could do. There were a couple more of these that we didn't get to that I wanted to do. What did we do? I wanted to do 20. We stopped with like 23, right? So maybe we could do like. Actually, let's just do 27. Let's do 27, 29, and 31. Let's do that right now. 27 is hard. So think about that for a minute. Maybe you'll just figure it out. 20, yeah, number 27.
What?
I think we should turn it into 1 minus cosine squared.
Yeah, that's
Okay, it's a great idea, except it's a terrible idea.
Yeah.
That's not what I was
Did
thinking.
they
I gotta think about that.
Yeah, that was actually Gabby's idea.
Wait, what'd you guys just say? Wait, what'd you guys just say?
So
Wait, Gabby, just tell me.
First of all, let's cycle through the possibilities. Let's talk about things that don't work. Letting u be sine, that just doesn't work. Because du is cosine, and there's just no cosine there. So fail.
Well, why don't you just make it into tangent?
Make it into tan?
Yes.
Oh.
Because if you take the derivative of that and you get cosine,
Or what do you mean by make it into tan?
because when you put cosine back in, never mind. Never mind.
Okay, so we could try to make this just 1 minus cosine squared. That seems like a not necessarily terrible idea. But then, I have no idea how to do cosine squared either. So,
Like 1 over cosine.
okay, you can try more weird trig crap, like, yeah, okay, so this is just 1 over secant squared, but like that's not going anywhere either. Okay, so something different is required. There is a trig identity which does not get the love and attention that it deserves because it doesn't come up that often until now.
Oh, that's
It's
guess.
impossible.
Arnold.
Do we, actually wait, never mind. That was, actually, wait, do we change this into like cosine of 2 theta somehow?
Yeah, that's exactly what we do.
Okay.
There is a so-called power-reducing formula. What are the power-reducing formulas? This is what you definitely learned at pre-calc B. We've used it probably like no times in the last year, or maybe once or twice. So it all has to do with cosine 2x. So I'll just assume you all know what cosine 2x is. What is that? Hope you do.
like
Three different ones for that.
Cosine, cosine, sine.
Oh my god.
There are 3 ones for that. Yeah, okay, so the basic one, maybe we should even take another step back. What is cosine A plus B?
Quite me. That's what I said.
Minus B. But that's not.
Okay, so that's correct. I'll just pretend that every single person said that or was about to say that. Okay, so therefore, what is cosine 2x?
Cosine squared
Cosine
minus
x.
sine.
Cosine squared x. Minus sine x.
Okay, so that is one, just like the analysis said, that is one formula, correct formula for cosine 2x. But then there are others which you can get by just like
Oh, one
yeah,
minus
doing
sine
things,
squared.
right? So instead I could get rid of the sign and I
Minus
could
2 sine
say,
squared.
you know, cosine 2x is cosine squared x minus 1 minus
Or not.
cosine squared x. And I get one of my 2 formulas for cosine 2x, which is 2 cosine squared x minus 1. At one point you had this memorized.
One is one.
And alternatively, you could sub for cosine here, right? So that's 1 minus sine squared x minus sine squared. Everybody with me? Just doing some like remedial trig here. So we get the other very important formula for cosine 2x. It's 1 minus 2 sine squared x. Okay, so everyone knew that. Sorry to waste your time. Well, solve for cosine squared. Okay, it's just 1 plus cosine 2x over 2. Right? Say right. Yeah, this is called a power reducing formula, and it is not used for much until now. Okay, we use this to reduce the power on a trick. Actually, it is used for a lot. This is how you derive the half angle formulas. You derive the half angle formulas by taking the square root of both sides of this line, and that gives you that. That's why cosine x is root 1 plus, or cosine x over 2 is root. Let's write this. If you take the square root of both sides and replace that x with an x over 2, that's how you get that cosine x over 2 is root 1 plus cosine x over 2. Is this familiar? The half angle formulas come from this line. Okay, similarly you can solve for sine x. So what's sine x?
1 minus cosine 2x over 2.
Yeah, sine squared x is 1 minus cosine 2x over 2. This is the other power reducing formula. And that's what we need to do in order to antidifferentiate this. Okay, so go, do it. I got that. What you got? Am I going too fast? Oh, I'll look at that mess up. I think I did mess up.
Wait, why is it only 1 half x?
I split it up. I split up this into 1/2 minus 1/2 cosine 2x.
Wait, what? When I did the substitution, I just put it back. I just put the 1 half back.
I don't know what to tell you. This is
Oh,
right.
wait, I
You
did.
have to split it up. You just split it up, right? This is just two things. This is just a 1/2 minus a 1/2 cosine 2x.
I did that.
And then that's just 1/2 x, but this one requires the use of. Are you with me? Okay, good. That was hard. Then we get to 29. All right, this is a notoriously difficult antiderivative. It's really, really hard. There is a long, complicated way to derive this that leaves you with some self-respect. Like, I could have come up with that myself. And then there is just a cheap trick, which you never would have thought of in a million years. Usually I like to do both. I'm running out of time, so I'm gonna give you the cheap trick. So here's the cheap trick. Aaron, here's what you do. Anyone could have thought of this. You just multiply the top and bottom by secant x plus tan x. Okay, go. That was your hint.
What's this reading?
You guys notice something now?
Oh yeah.
What do you notice?
I noticed that when you multiply them out, it looks good.
Looks good, yeah. Why does it look so good?
Because it's because secant squared x is like net derivative of tan.
It is the derivative of tan, secant squared x.
Yeah, and it's secant x tan x the derivative of something else.
Cosecant.
Yeah. Wait.
No,
No.
secant.
Secant.
Yeah.
Yeah, so in fact, this secant squared is the derivative of tan. Secant x tan x is the derivative of secant. Thus the top is just the derivative of the bottom, right? You guys don't seem that. You guys don't seem as excited about this as you should be. Yeah, so let u be act for the camera. U is, so if I let u be secant x plus tan x, then just like freaking magic, du is secant x tan x plus secant squared x dx. In other words, exactly the numerator. So this just converts directly into a du over u problem. Pretty cool. Final answer, ln, absolute value, secant x plus tan x plus c. Done. All right, there's a less cheaty way to do this, but this is how most teachers teach it. That's just this one thing, like, yeah, that's just how you do it. That's just how you have to know how to do it. All right.
Take it.
Amy, I'm done with direct instruction on anti-differentiation. But you are just only maybe 40% through your life of anti-differentiation. You're going to get a lot better at this. You're going to get a lot better by just practice, just doing so many of these problems over and over again. Then you just get really good. For that, you have a Wallops packet. So I'm ready to just like stop, and we're going to do something totally different now. Any objections? All right. Today we begin a very exciting. So what we're going to do right now, and for the rest of the period, is something really, really exciting. And that is, we are going to start the second half of this class. And what is the second half of this class? All about?
Area problem.
Yeah, solving the area problem.
I've been waiting.
You've been waiting for this? All right, good.
Not actually.
So the area problem is this is the other problem that Newton had. Find the area under a curve. For this I have a packet.
The child style of education.
Yeah.
Turn it up.
Alright, by the way, why do I want to solve the area problem? Can we get a quick reminder of this? What is the area problem mathematically? Candia, what's the area problem mathematically? Just state, what is the area problem?
Find the space between lines.
Find the space between lines. Okay, yeah, kind of. More specifically, find the area under some kind of curve. I have some sort of function, and I'm at some interval, and I'm on some interval, and I know the function. The goal of the area problem is find the area under the curve. Okay, that's a mathematical statement of the problem, but that you miss the whole point of calculus if you're just doing that. What is the point of the area problem? What? Yeah, you should probably like turn the camera. Yeah, what is the point of the area problem? Why do I care about the area problem? Yeah, Arnold.
Because if you have like a velocity versus time, and you multiply them together, you get the area under the curve.
Yeah, that's right. If you have a velocity versus time graph, Newton said, hey, look, suppose I know on some interval, precisely at every single second, how fast I'm going. By the way, can you think of a situation in physics where I would know how fast I'm going, yet not know where I am?
Space?
What?
Space?
It's not really an answer.
In a submarine? Under the
Can
sea?
you stop being yourself?
Oh.
Why? Can I get real answers? This is a deep question.
When you don't have like a GPS or something?
No,
you're
man,
just flying.
seriously. When would I know velocity?
Is that what happens with like electrons?
Wait, you don't
Is that what happens with electrons?
Oh yeah, you know the speed of those ones is very
Playing.
Oh yeah, like
Okay, yeah, I guess. Okay, I was thinking more.
Guys,
Okay,
that's
let's try it again. Let's take it back. When might I know acceleration but not know velocity or not know position?
You're dropping something.
Yeah, when I'm dropping something. In fact, all the time in physics, I know how fast something is accelerating without particularly knowing how fast it's going, because maybe I know what kind of force I'm applying on the object, right? Since F equals ma, if I apply a particular force to an object, then I will know immediately, because I'm causing the force, I'll know what the acceleration is, yet I might not know the velocity. Okay, and this happens with velocity also. Maybe that was a little hard or vague. Alright, if I have a velocity versus time curve, what Arnold says is, and we did this on the first day of class, if I can split up this time interval into little time intervals, and I take the area of this rectangle, that represents how fast I would be going on this interval, approximately, assuming constant speed. And if I add up all these rectangles, what I get is an approximation of the total distance traveled. Because if you multiply a time, distance equals rate times time. And the rate I'm going is my velocity, that's the height of the function, and the width of the interval is the amount of time that's elapsed. So if I multiply this amount of time by this height, then the area of that rectangle represents the distance traveled. Assuming I was going at a constant rate over that interval, which is not quite true. And then the area of the second rectangle represents the distance traveled, assuming I was going at that constant rate, which is not quite true. So you add up all the areas of all these rectangles, you get an approximation for the total distance traveled. Okay, and that's a physics problem that we want to solve. All right, so let's do it. I gave you a particular problem. Let y be negative x squared plus 5 from x equals 0 to x equals 2. Alright, this is a little bit tedious at first, but I think that this is a tricky topic, so I want to kind of go very slowly, although I also want to finish. Let's make this picture. I'm gonna make it on the board. Sorry. Let's see. And I think I said, let's see, what did I say? Approximate the area between the x-axis and the curve y equals negative x squared plus 5 from x equals 0 to x equals 2. Divide the interval from 0 to 2 into 5 equal width subintervals and approximate the area using rectangles that lie alternatively below and above the curve. Okay, so if we're going to go from x equals 0 to x equals 2, but I want to split it up into 5 equal width subintervals, then what's the width of each subinterval? 0.4. And I think that's how it's already split up on the paper, right?
Yeah.
So we do one at 0.4, one at 0.8, one at 1.2, one at 1.6, and one at 2.0. And at 2.0, the function is 1 high, and at 0.4, the function is, well, I don't know. Actually, I don't care.
Wait, how are you
So what we have is
Oh, you do a line.
something like this, and the area under this curve is what I want. Okay, and the first thing they said is find a lower estimate. If I want a lower estimate, how should I draw my rectangles? Draw some rectangles. Draw 5 equal width rectangles in such a way that you are getting an underestimate of the true area. Yeah. What I'm now going to do is I'm going to use the right endpoint. So let's see what I'm doing here. I'm going to use a different color. So now I will use the right endpoint of the subinterval as the height of the rectangle. And again, I go to 0.8. I plug the number 0.8 into the function, and whatever y value I get, that is going to be the height of that rectangle. So I'm using the function, but I'm using the value of the function at the right endpoint as an approximation for the height of the rectangle on that subinterval. Everybody with me?
I love
So yes.
that.
Okay, good. So let's let's figure out what all these points are, first of all. And let's use fractions, because I think this is easier. So let's take this point 0.4. What is, can I get these coordinates? So if we use fractions, this is like 2/5, and then this is, let's just write f of 2/5.
Oh, 121.
Okay, yeah, we'll get to that later. So this is 2/5, comma, f of 2/5. How about the next point? What's this?
4/5.
Okay, obviously it's 4/5, but now I kind of want to come up with a pattern because I want to do this with a pattern. So what can I say about this 0.8? Well, yeah, it's 2/5, but what happens with each subinterval? I skip over by 2/5, right? So this is 2/5, and this is like 2 times 2/5, comma f of 2 times 2/5. So. You guys see what I'm doing? Somebody with me? Okay, how about when I go over to 1.2? How could I write what these coordinates are?
4 times?
Wait, what? Now this is going to be 3 times 2/5, comma, f of 3 times 2/5. And this point, 1.6, is 4 times 2/5, comma, f of 4 times 2/5. And the final point, don't zone out, stay with me, this is actually pretty hard, alright? So, yeah, good. 5 times 2/5, comma, f of 5 times 2/5. Alright, and, okay, of course that works, because what is 5 times 2/5?
2.
It's just 2, so everything's good. And I could even make the pattern even more explicit by writing my first one as 1 times 2/5. Okay, and I could even make that first one, what is that first point over here? I could even call that 0 times 2/5, comma, f of 0 times 2/5. Okay, because the goal here is to come up with a pattern. Alright, so, what is the total sum of all of the areas of these 5 rectangles in this case? Let's just write it out. What's the area of the first rectangle? So it's just the width times the height. And the width is? 2/5, and the height is? F of 1 times 2/5. Everybody with me?
Should we write this down?
Yeah, you should write this down. What is the area of the second rectangle? Everybody. What's the width?
2.
2/5, right? 2/5 is the width. Times, what's the height of the second rectangle?
F of
2 times 2.
F of 2 times 2/5. What's the area of the third rectangle? 2/5 times F of 3 times 2/5. Okay, and like we can just keep doing it. Let's just finish it off. 2/5 times F of 4 times 2/5 plus 2/5 times F of 5 times 2/5. Okay. So here I am, just sort of tediously writing out the areas of these 5 rectangles. Do you see a pattern here?
Yeah, they're 2/5 for all.
Yeah. Can you write this for me now in sigma notation? Yeah, you can.
It's 2/5 sigma.
So first of all, every
Oh,
one of these
and-
terms has a 2/5. So I can just factor out a 2/5. And then it's going to be the sum.
F of n times 2/5.
I equals 1.
Yeah, I'm just going to use an I because I don't know, just because.
of the sum.
So let I be 1. And when does I stop?
5.
At 5. And what does each term? What is each term?
F of I times 2/5.
F of I times 2/5. Yeah, so if you understand sigma notation, then of course that long thing that we wrote first just is exactly that. Okay, and the goal of kind of writing it out in this particular way, which leads to the pattern recognition, is so that I can now use my, my sigma notation formula. All right, good. So now we just keep going. So this is 2/5 times the sum from I equals 1 to 5. Well, what is the actual function in this case? It's this, right? So now I'm going to plug 2/5 I into this function, and I get negative 2/5 I squared plus 5. Because that's just what F is. Bronte, with me? Bronte, with me? Good. All right, so now we keep going. Multiply this out. What do we get? 2/5 times the sum from I equals 1 to 5 of, do it man, do it. What is this?
4/20.
Negative 4/25 I squared plus 5. Now, in this case, because there are only 5 of them, it would have been easier for me to just add them up, like by hand. But we're trying to practice something, so we're actually going to use these formulas. And so what I'm going to do is I'm now going to split this up into 2 different sigmas. One of them will be factoring out the negative 4/25. I get negative 8 over 125. Seeing where this is going? Sum from I equals 1 to 5 of I squared plus, you tell me.
Plus like 25 times 2.
Times 25.
I think it's just 2, right? I don't know.
I don't think it's.
No,
I don't
it's not just
believe-
2
I
because
think it's
don't you
10.
add it like
If you factor out the 5. Yeah, so it's just 2
oh.
sum.
Isn't it 10? Because you have to add 5 times.
Yeah.
Okay. I was doing this.
Oh.
Or just 1 actually. But yes, it is just 10. But I'm just saying, I'm just distributing, I'm using just properties of sigma notation, which says that you can split up a sigma into like 2 different things. So, and then, but yes, you're right. The sum, 2 times the sum from I equals 1 to 5 of 1, that's just 1 plus 1 plus 1 plus 1 5 times. So yes, this number does turn out to be just 10. Okay, what is the sum from I equals 1 to 5 of I squared? Okay, obviously you could just add 1 and 4 and 9 and blah blah blah, but we did a whole thing in pre-calc C. What is the sum from I equals 1 to n of I squared? Does anyone remember?
N times n minus whatever.
No, that's the one.
I thought you said I.
N minus,
This is n, crap, do I know this? N,
1 minus.
n,
N plus
N
1
plus-
plus 1.
yeah, that's right, n plus 1, 2n plus 1 over 6. Yeah, n plus 1, 2n plus 1 over 6. This is a formula that we rederive. I'm actually about to do that today in functions. Okay, so therefore, what is the sum from I equals 1 to 5? So I get negative 8 over 125, and this is going to be, what's this? Sum from I equals 1 to 5 of I squared. Well, that will be, according to the formula, n is now 5, it's going to be 5 times 6 times 11 over 6 plus 10.
55.
Now I can do some cancellations. The 6 cancels, the 5 cancels the 125 and makes a 25. So I get negative 88 25ths, someone back me up, plus 10 25ths, or 10 times, well,
250.
this is 250 over 25. And so my final answer is 162 over 25. Right? So that is, 25 goes into 150 6 times. So that's 6 and 12 25ths. So that's 6.48. All right. We just calculated that the area under this curve is 6.48 as approximated using a lower estimate. Everybody with me? All right. Well, what should we do next? Yeah, oh, because it says it on the packet. Now let's get an upper estimate. So we're going to do this problem all over again. Don't wait for me. Start. Okay, so this time, if we want an overestimate, then we have to draw the rectangles differently, right?
Just start at 0.
Exactly. So picture's worth 1,000 words. Everyone see how now by drawing the rectangles like this, I'm going to have an overestimate, right? Okay, so now we go through this process again. What are all these points? Well, this is 0 times 2/5 times f of